Look, this is not the level you need to be working. We need to be above this. And the only reason why I'm having to explain this is because, and I don't say this lightly, some of you refuse to figure this out. Meaning you're not taking the proper time at home to come up to the level you need to be. There's nothing new here. So let's, and I'm going to blaze through it because there is nothing new here. I see three forces acting in this system. Three forces acting in the system: normal force, friction, weight. All right, that should be fast. Remember, when we're doing this, the free body diagram is in service to you. And what I mean by that is you're just using it to solve the problem. It's as useful to you as you need it to be. I don't need to draw the free body diagram anymore. Not for a problem like this, but you probably still do. It should be serviceable. But it's an incline. It's the same every time. I'm going to pick a direction, call it positive. I have no need to pick that direction, except that I said yesterday we're going to have this thing sliding down the ramp and want to figure out what its acceleration is. So I made this the positive direction. I think it's accelerating down the ramp. That necessitates the y direction being like that. So I'll make this positive y. I've got one force that is off axis, so I will take it and break it up into two. This is our 40 degrees. That makes this mg sine 40 and this mg cosine 40. The ramps are the same every time. Unless you change your coordinate system, this will always be how you set this up. So all of you who don't know that, know it by tomorrow. All right? It's daring me to maybe turn this into something you have to do within like 60 seconds to see if you've memorized the parts of this that can just be memorized. Because there's a lot of this that can just be memorized. I don't say this lightly, but this is a net force equals ma problem. Not because I don't think it's traveling at a constant speed, but because I don't know if it's traveling at a constant speed or not. I don't really know if this object would speed up or slow down or travel at a constant speed under these conditions. And I reminded you that you choose Newton's second law when you don't know. So unless you are told it's stationary or traveling at a constant speed, you have to choose Newton's second. But the way I set this up, the net force in the x direction is what equals ma. The net force in the y direction equals 0. This is just normal equals mg cosine theta. That happens a lot with ramp problems, right? There's only two forces in the y direction. They have to be equal and opposite. Again, we've done this a lot. In the x direction, I've got mg sine theta minus friction equals ma. Pretty straightforward. Now, that's Newton's laws. That's all Newton's laws will do for you. But that should be quick. It's taken me 3 minutes to write this down, and that's with all the talking and stopping. I expect that you can get to this point in like a minute. When I'm timing a test, that's my expectation. So get there, memorize it, okay? You can do this, you can practice it. You can practice getting to this point. In fact, there's more to go, but it's really not that much. It's the same thing every time. There's friction here. Friction is equal to mu times the normal force. This shouldn't require a lot of thought. That means friction is going to be equal to mu mg cosine 40. So ultimately that means mg sine 40 minus mu mg cosine 40 equals ma. And this is why you didn't need the mass. Do you see why you didn't need the mass? You should. You should see that mass is in every one of these terms. So mass is unnecessary. This shows up a lot, some combination of this where either you're subtracting them or if they're in the same direction, you make them both the same side. Excuse me. But whenever you subtract one thing from another, you have the possibility of your answer being positive, negative, or 0. you now know the conditions for whether it's speeding up, slowing down, or not changing, right? Those are your three possibilities. If these two things are equal to each other, the object travels at a constant speed. However, if it's positive, then it travels in the direction you chose as positive, down the ramp. If it's negative, then this force is slowing the object down if it's moving down the ramp. All things that you should be able to figure out by looking at this, but this is pretty straightforward. Plug your numbers in and you'll get 4.5. I'm not really interested in this problem. And I know you are, it's in your homework. And if I was to give you a quiz tomorrow on it, I'm afraid that there'd be a bunch of you who would not score well. But is there anything new on the inclined plane problem? So, prove that. I'm giving you exactly 3 minutes before I call on the weaker of the people in the room. And I don't mean that mean. I mean it because I want them to be the ones working hard here, but not that hard. You have whiteboards, actually. Here's what I'll have you do. I want the answer on the whiteboard. Just the numerical answer circled. You're at your table. Make it happen. Let's say there's a coefficient of kinetic friction of 0.25 and 20-degree ramp. I give the box an upwards kick, so it's moving 4 meters per second up the ramp. How far does the ramp go? I'm sorry, how far does the box go before it stops? That's what I want to know. How far up the ramp does the box go before it stops? I want the number in meters. If you understand the ramp problems, you can do this one. So you sense my frustration now? Let's talk about what you may or may not have done. I hate to do this, but I probably will have to. One of those. One of these. One of these. So normal, friction, weight. Did you do a coordinate system this way? I'm gonna make that the positive direction. And a coordinate system this way. I'll make that the positive direction. Any questions? Yep.
So you kicked the box up the ramp?
I give the box an initial velocity of 4 meters per second up the ramp.
So that wouldn't be an applied force?
It is not an applied force, it's a velocity. Any question about my choices? All righty. Is this what you did so far? So did you then go the next mile and break this up into its components? All of this the same so far, right? Haven't changed a thing. So do you have mg sine theta here and mg cosine theta here? All right, so net force in the y direction equals 0, so normal equals mg cosine theta. All good? And that means, of course, that friction has to be equal to mu mg cosine theta. Still good? Net force in the x direction equals ma minus mg sine theta minus friction equals ma, because mg sine theta and friction are in the same direction. All good so far? All right. So minus g sine theta minus mu g cosine theta equals a. All right, you just type that in and get your 5.7 meters per second squared. Is that what you guys got? I mean, because that's the next thing here. This should be negative 5.7 meters per second squared. I'm afraid that if you made this mistake, and there might be one here, let's fix that now. Even if you made down the ramp positive, you would have positive 5.7 because the friction and the weight are in the same direction. Calculator's all in degrees, I assume. So once I got here, the next thing is initial velocity is positive 4 meters per second. It's up the ramp. Final velocity is 0, acceleration negative 5.7 meters per second squared. You're looking for delta x. I assume v squared minus v naught squared equals 2a delta x. So you will get delta x equals 1.38 meters. There was a correct answer in the room. It just wasn't many of yours. I don't know where your mistake is, but do you understand why I find it a little frustrating that we're having a mistake on this one? Where's your mistake? Did you find it? Is it in your ability to push buttons? Is it something you set up wrong? Or are you fundamentally flawed in your thinking on this problem? There's a lot of places for this to be an issue. I'm hoping it's not a fundamental flaw. But do you see anything really different between this problem? You need to be practicing. No matter which time, from time equals 0 till the object stopped, the forces were always the same, right? The weight never changed, the friction never changed, the normal force never changed. This is example number 4. Still Newton's second law problems. Drag forces are generally forces that are proportional to the velocity. They come in a variety of types. There's linear drag forces, and there are quadratic, and they can be more than that. There's all sorts of different kinds of drag forces. It really depends on the type of drag. There's laminar drag and there's turbulent drag, and it can be complicated. Ultimately, what I need you to understand is that drag forces are forces that are proportional to the speed of the object in some way. The value of k here is an arbitrary constant. I went into great depth about what the k value means in 6th period, not meaning to. But the value for k is actually an amalgam of a lot of things. If we pick just one of these to look at, and I'm going to pick this one for a moment. The value for k represents many properties. For example, part of what k represents is the viscosity of the fluid. You would have a different value for k if you're trying to pass through molasses versus pass through air, right? You would probably have a larger value for k if you're trying to pass through molasses than air, because molasses is more difficult to get through. You would develop a stronger force quicker under lower velocities than you would if you're trying to go through the air. Does that make sense? So for the same value of velocity, there's more drag in molasses than there is in air. Does that make sense? But it's not just that. Your surface area makes a difference. If you have a larger surface area, then you're probably going to generate more drag than something that has a lower profile, right? A more streamlined car versus a more flat-fronted car, they're having different values for k. K has lots of things in it. And so it's not just one thing. We reduce it to a single variable as to not be distracting, but the truth is the aerodynamic coefficient is a bunch of stuff that has to do with cross-sectional area, the shape of the object, all that kind of stuff plays a role in it. But we just call it k. Does that make sense? It's a single variable that indicates that the big deal is that this force is proportional to how fast you're going. It could be how fast you're going squared, it could be how fast you're going cubed, some function of the velocity. The negative sign there is to remind you that the force opposes the direction of motion. So if you're moving forward, this force acts against you. That means its direction could also be changing if your object's direction of motion is changing. So if you hit a ball through the air, the direction of drag is changing all the time because the object's traveling in a parabola, or not because it's experiencing drag. We're going to only do one-dimensional problems here. And so for this one, I want you to consider that the thing that makes this an interesting problem is that it doesn't stay the same. In this problem, at t equals 0, if I say I'm going to drop the object, and the object we're going to use here is a coffee filter because we're going to do this lab next week. Coffee filter labs, they're great. They have a lot of drag. They have a lot of cross-sectional area, and they have low mass. So they generate a lot of drag force for their size. And you can nestle 2 or 3 together, so it's easy to double the weight or triple the weight or quadruple the weight. You follow what I'm saying? So we're gonna do a drag lab, and they are shaped so they usually produce laminar drag, meaning they part the air in a nice laminar layered flow. So you get this kind of relationship. All right? That's why we'll do that lab. Here's what I want you to think about. At T equals 0, when you drop the coffee filter, the only force acting on the coffee filter is the weight of the coffee filter. Right? At T equals 0, it's not moving. So the drag force is equal to 0. Right? It hasn't moved yet. Is this balanced or unbalanced? Unbalanced. So is the object going to accelerate or stay moving at a constant speed? It's going to accelerate. Its velocity will change. So in the next moment, although the weight will not change, it now has a downwards velocity. Doesn't have to be much, but it has a downwards velocity, so that produces an upward force of drag that is proportional to the velocity. I'm not putting the negative sign there because I drew the arrow. You follow me? That's why I didn't put the negative sign. It's upwards. It opposes the direction of the velocity. The negative sign is just about direction. All okay? Now, is this balanced or unbalanced? Still unbalanced. So a few moments later, the object's weight still not changing, but it will have increased its speed because it's unbalanced downward, so the velocity is greater. But here's the question. If it's moving faster, is the net force staying the same, or is the net force changing? The net force has to be changing. The kV part is getting bigger. So it's not accelerating as much, because now the upward force is bigger than it was a moment ago. Eventually, you will reach a steady state condition. I think guys can kind of imagine that if this keeps going the way it is, although the weight's not changing, eventually we should reach a point where the upward force equals the downward force. This is a special condition known as the terminal velocity. And this occurs when you finally reach the condition that net force equals 0. Objects experiencing a velocity-based force have an acceleration that is always changing. Terminal velocity occurs in situations where there's something that is propelling the object. Eventually, if you propel something, it will reach a velocity that will generate a net force of 0. But also, you can have something that you just push across the floor. If there's no friction, all things eventually come to rest anyways because they experience drag. So the drag force is a force that is proportional to some function of the velocity. And analyzing this is a little bit challenging. There are some things I want you to be able to do. 3 checkpoints I specifically want you to be able to do on problems that have a velocity-based force. The first one is you should be able to see if there's going to be a steady state condition. Is there the possibility of a net force equals 0 for the situation that is set up? Not all situations will have this. Some will. So an example is if I have a box on the ground, that's not a box on the ground, but let's just say that's the ground. If I have a box on the ground and I give it a starting velocity in this direction, and I tell you that this is the initial velocity, if it's experiencing drag, it won't reach a steady state condition. It will experience a force this way that is proportional to the velocity. It will eventually just come to rest. This situation doesn't have a steady state condition. Now, if instead I tell you that some guy is behind the box pushing on it, well, then he might be able to push it fast enough to reach the steady state condition. Right? The steady state condition occurs when the net force equals 0. So your first thing I want you to know is, or the first checkpoint I want you to be able to reach is, can you reach the checkpoint and find out if there's a net force equal to 0? The next checkpoint I want you to reach is I want you to consider something in the middle. Pick a middle circumstance. something where the object has not reached terminal velocity, but does have some of the drag force, and set up a force equation. All of your problems will be one-dimensional, that helps, but set up a force equation. This one's pretty easy, but I'm going to choose purposely to make downwards the positive direction. That means my net force is going to be equal to ma, and my acceleration is downwards. My two forces will be mg and kv for this problem. So I want you to be able to set up a net force equation for some point in the middle. This is to help us understand that there is the possibility of a steady state condition. Look to the future of where the steady state condition is. The steady state condition occurs when mg equals kv. In fact, it wouldn't be too much to ask you what the terminal velocity is. Now, something to keep in mind. Anybody ever watch skydivers or seen like skydiving videos? Right, have you ever seen them? Skydivers can manipulate K while in flight. They can change their terminal velocity. If they spread out, K becomes a bigger number. Their terminal velocity gets smaller. Now, they're still falling the whole time. They're never stopped. They're just changing the rate at which they fall. So that's why you'll see them separate from their friends when there's a group of them, or you'll see them tuck themselves in if they want to go faster to catch up with somebody who's further down than they are. They're falling the whole time, but they're manipulating their relative velocity relative to each other. Right before they land, they make this really, really big, right? They knock their parachute out and open it up. The parachute expands, creating a huge surface area, making their K a maximum value, reducing their terminal velocity by a lot, so that they slow down to as slow a speed as possible before hitting the ground. Right? The terminal velocity is all right there. There's something else I want you to be able to do, but this is harder. I want you to be able to create a differential equation from this. You guys who have finished a round of calculus should be able to solve this differential equation, but you guys who haven't, you should be able to set up the differential equation. And I'm saying this because we know about a couple of differentials already. We have these two differentials. We know that A is equal to dv dt and V is equal to dx dt, the two differentials that you were learning about earlier in the year. To create a differential equation, all you have to do is substitute in a differential for one of your variables. But there's a right answer here and a wrong answer, and I'm telling you right now what you need to do to get the right answer. To create a differential equation, whenever you're using Newton's second law, you're going to replace A with its differential form. You need matching variables. And the only variable we can get is to replace A with dv dt. When you do that, you get a differential equation that's in terms of V and T. These are the three checkpoints I want you to be able to make it to. I want you to determine what the terminal velocity is. I want you to set up a force equation for something in the middle, and I want you to create a differential equation. Now, I'm going to ask you to solve this differential equation. You're going to have to learn how to do that. I think that's a lot to add to you right now. So I want these three checkpoints reached on any problem that you're facing right now in your homework. But eventually, I want you to solve this. All right, you have to do the math to solve it. This one would be potentially challenging for most of you, unless you've had a course in calculus already. If you've had a course in calculus, you should be able to produce V as a function of T. That's what solving this differential equation is about. You see, we can't study this like we did the other problems. The acceleration is not constant. Because the acceleration is not constant, the motion equation for this is something weird. In fact, this one is an exponential decay. It looks something like that. So I want you to understand that the answer to this is not straightforward. But I want you to reach these three checkpoints. I believe you can reach these three checkpoints. Everybody understand what I want you to be able to do with this? I want you to be able to set up the Newton's law problem somewhere in the middle. I want you to find, if it has one, the terminal velocity, and I want you to be able to set up the differential equation. It's not hard to do. Those are your 3 checkpoints. So you have a couple of these in your homework. Make sure you try them. All right? The last thing, and what part of your lab is based on tomorrow. I want to talk about whenever velocity is changing, but not the way you're talking about. Situations What do we do when we have situations where we have a force that causes a change in direction and not speed? This sounds arbitrary, but it really isn't. In order for us to change something's direction without changing its speed, there's only one way to do that. You see, if we have an object that's moving in a straight line, let's just say we have some object with a velocity this way, and for our object, we'll just have a ball. Just a ball in space. If I want to change its direction without changing its speed, I have to be very careful about how I apply a force to that object. If I apply a force this way, say this is the velocity here. If I apply a force this way, part of this force is in the direction of motion, and part of this force is to the left. This force will make the object travel faster over time because part of the force is directed in the direction of motion, and part of this force is going to cause the object to move to the left. If I want to only change its direction and not change its speed, then I have to more carefully apply this force. In fact, I can't just do it at some random angle. I'm going to have to make it so that it is perpendicular to the velocity. That's the only way I can do so. It's the only way I can make it so that the force only changes the direction of motion. The problem with that is that's exactly what it will do. It will cause the object's path to change as the object builds a velocity that's to the left. But this force doesn't change the speed. Well, I'm sorry. This begins to change the speed. Let me say this different. This begins to change the direction, but it also begins to change the speed as it adds a component of velocity in this direction. So if I want to only change the direction, I'm going to have to, when I make it over to here, make sure the force stays perpendicular to the velocity. Otherwise, it will make the object change its speed. It'll make it speed up. If I always left the force in the same direction, what I would have is a projectile, right? That's what would happen if you rolled something off a table. This wouldn't be just changing its direction. It would be making it go faster and faster as it got closer to the ground. So I want to make sure that as the object turns, I turn my force too. So give it a few more seconds. The object's path turns a little bit more. That means its velocity has changed direction even more. And that, of course, means that I have to have a force that's changed direction even more. Now, if you're getting a picture of this, what you should be noticing is that all of these forces point to the same place, right? They point to the center of motion, or what we call the center of curvature. This force, because it always is changing and is always pointing towards the center, is called a center-seeking force. The word for this is centripetal. Now, I don't like to say centripetal force.
I will, but I don't like to say centripetal force for a number of reasons. This is not a new force. Something in nature causes this force, and the object travels in a circle. So it's not a new force, but you'll see it listed as a force. What I like to say is that there's got to be a force in nature that causes a centripetal acceleration. That's what I like to say. And that's what I will want you to put in your notes. Is that if you want an object to change its direction and not change its speed, then you need a force that points towards the center of curvature. Something in nature has to cause this force. Let's take a look at some examples here. First, imagine something that travels in a circle. Tomorrow when you do your lab, it's real simple. You're going to have a stopper tied to a string, and you're going to swing it around your head. It produces great potential accidents. I love watching this lab from afar. So I will stand up here while you guys are all swinging these weights above your head and trying to measure something. It's a lot of fun to watch. A lot of fun. But I want you to imagine what this looks like from the standpoint of your lab. I give you a little tube. And some string. So you hang a weight down the center and pull a stopper on the end, and the stopper spins in a circle. Can you imagine this? Right? Can you have it in your head? This is like you holding it and you're doing it right above your head. Got it? So top down, what this looks like is pretty easy to see. You've got a circular path. There's a string. And then there's the stopper. The stopper has a velocity like this, but the string has a tension acting on the stopper in this direction. For the stopper to travel in a circle, the tension has to always be directed towards the center of the circle. This object will have an unbalanced force. It is accelerating, right? Has to be accelerating because it's changing its direction. Its speed isn't changing, but its direction is changing, therefore it's accelerating. I'm going to give that acceleration a special symbol, a little C next to it, to remind us that this acceleration isn't about change in speed. This acceleration is about change in direction. In fact, we're going to call that a centripetal acceleration. In the case of this problem, the unbalanced force is tension. Tension is what causes the centripetal acceleration. For your cars, what do you think causes the centripetal acceleration on your car? I know you want to say tires, but that's not it. It's friction. You turn the tires, but if there was no friction, would your car turn? Just go in a straight line, right? Your car turns because of friction. You make the tires at an angle, friction pushes on the tires, and that pushes the car to the side. It is friction that makes your car turn. For the same reason that friction makes your car go. Tires spin, but you want the tire not to spin in place, so friction pushes on the car. Friction is what makes your car go and turn. Here, tension's making this go. It is important that you understand that calculating this acceleration is different. For us, it's this ratio. It's the square of how fast it's going divided by the radius of curvature. Right, remember, it's not speeding up or slowing down, so we need a different way of calculating the acceleration. This is how it's calculated.